And we got the recording going. Thank you, Ellie. And we will, I'll just take the first group who wants to volunteer to go.
We do.
Okay.
If I can find it. Okay. All right, hopefully y'all could see my screen. We are going to be talking about an AR to install VFDs on condenser water pumps. And we are the Upward Slopes LLC, and that is why we have such an amazing logo, because we love skiing and snowboarding. And Nathaniel is our president, and for this presentation, he worked on the cost methodology. VP of Communications is Nathan. He worked on savings methodology. Operations was Jace, and he is doing the AR description. And then I'm VP of Quality, and I'm doing the intros and questions at the end. And Marla is also VP of Quality, and she also worked on cost methodology.
Awesome. Thank you, Brooke.
Well, so the condenser pump VFDAR, the current situation, there are two pumps. There are two condenser pumps that are in a lead lag setup, but there's no logic between the two. So it's kind of a manual lead lag system, and neither pump has a VFD. So what we're proposing is that we want to add a VFD to both pumps, because VFDs increase the efficiency and the longevity of the motors, and ultimately just introduce consistency that can save money, so that the pump's not just jumping from 0 to 100, but can save money by being consistent.
Awesome. So as you can see here on this pump curve, this is just a dummy pump curve from a different assessment, but you can see that as you lower the speed of the motor, the RPM, it decreases both the flow rate and the pressure of the water, the head. So in installing a VFD decreases both of those, which lowers the power usage. However, the drawback is that a VFD does consume some energy, and also you have to increase the operating hours to achieve the same water supply. But overall, installing a VFD is usually pretty effective at decreasing the energy usage of a pump. Go to the next slide. So these are a couple of equations we use. When you decrease the pump speed, you can use the affinity law to solve for the new water flow that will come out of that pump. And so here you just plug into that first equation to get the new flow rate, and you can use the pump curve to determine the new efficiency of the pump and also the new water pressure. Then we have here this power draw equation where you can plug in the water head, the flow rate, and all the different efficiencies in order to solve for the new power usage of the pump. Go to the next slide. So here are some equations. We put these in here for the group who's doing the AR to hopefully be able to make their life a little easier. You solve for the new operating hours by using the ratio of the old flow rate to the new flow rate and multiplying that by the new, or by the old operating hours. And then you use the new power draw and multiply by the rates in order to get the new, the cost of energy and stuff. Now, the thing that is kind of interesting is that the demand charge depends on if these pumps actually contribute to the peak demand. So we need to consult the utility data in order to see that. So it's possible that, they don't actually contribute at all, and at the peak demand time of the day, these pumps aren't even being used. But if they are being used, it can be pretty effective at doing energy saving. So that's something to look out for if you are trying to work on this AR. Next slide, please. So here we wanted to put some assumptions in to just get some actual numbers. We assumed that looking at some of the notes that some of the people in the IC did at this assessment, they said that during the summer, some cooling towers are on, so the pumps aren't used as much. And so we assumed that because they're on off, they operate on off, they're going to be on for half of the time they're needed, and then 0.8, so 80% of the year, because we're ignoring some of that summertime. So we get their current operating hours from that assumption. We assume that we're going to decrease the pump speed by 25%, which using the affinity laws lets us solve for our new power. Now, I think that the power equation that was shown previously is more accurate, but if you don't have all those, the flow rate and the pressure and things like that, you can use the affinity law and it still is a pretty good answer. And so here we assume that because adding a VFD decreases the efficiency, we're going to have about 55% of the current power will be the new power after implementing these VFDs, but the pump will be used 25% more. So if we go to the next slide, we show you some dummy calculations we put in. Here we have our 3 pumps. I think there are 2 main pumps, and then maybe there's one for backup. So if you have the 3 pumps in there, convert it to kilowatt hours, you can solve for the current charge. And then if you have the new power, you can solve for the new charge. And as you can see at the bottom there, you save about $5,000 a year. And it's quite possible there would be demand charge savings, but we don't know that. And so we put that here on the slide.
Okay, so for implementing a VFD, if we were to do that, it would lower the flow rate of the pump, and then that leads to a decrease in efficiency. But even though the efficiency is decreased, the overall power is decreased. And so then when we implement a VFD, we need to take account of the 3 pumps and the cost of each VFD, and then the installation costs. So then I came up with the equation. So for every horsepower, it's $200, and then you would just multiply it by the horsepower of each pump, depending if they have different horsepower, and then the labor cost and installation is the factor of 1.5, and then the payback would be the total implementation cost divided by the total annual cost savings.
Alrighty, and so the cost methodology for the facility is that currently they don't have many VFDs on their systems. They have a few for like their cooling towers, their cooling tower fans, but for these other systems, they don't actually have anything. So the implementation costs will definitely be dependent upon if the VFD is applicable for that system. And as Marla stated, the minimum is $200 per horsepower, with the maximum being about $500 per horsepower unit. And if it isn't applicable to the system, that being the VFD, there would definitely be a greater cost because you have to replace the system and make it applicable for that. So an estimation of that would be about $39,000, $37,000 coming from that 500 times the 3 VFDs and the 25 horsepower of each compressor unit, and then the $1,000 for the VFD itself. And then there's just a slight reference right down there in the bottom, just going off of VFDs.com, which has a lot of useful information on that.
So some of the recommendations would be to make sure if any of these pump ARs seem possible, always ask if there's like pump curves that they have available, that you can make sure you get it. And really important to make sure you take a picture of the pump and the motor nameplate, not just the motor nameplate, but also the pump nameplate. And then it's good to ask for or log the pump flow rates and power as well. So some questions we would like to consider is, how would you find the pump curves from the nameplate if the facility doesn't actually have them available? Also, potentially I could have worded this better, but are you screwed if you forgot or missed or couldn't find the pump nameplate? Also, what are your thoughts on including demand savings, and then thoughts on appropriate use of the affinity laws? So we'd love to get some advice or thoughts on those questions.
So before we jump to answer these questions, we're talking about putting a pump on a VFD on a pump, and the cooling tower already has a VFD. Is that correct?
Yes, that's correct.
Okay,
Like, just to clarify for everybody, Sunny, the cooling tower fan has a VFD.
yeah,
Yes.
the cooling tower fan. Okay. So on this project, two things you need to be aware of. When you make two things variable, you have a tough time controlling to a set point, right? Your control parameter can start fighting with each other. Sorry, I have a bad cold. So you need to be careful about varying flow and varying fan. What will happen there is you'll have too little water and it's too warm. Because what is your control variable? Some set point temperature, right? So you need to think about that. Not saying it can't work, but just keep that in mind. Next thing, go back to the pump curve slide. I want to cover one topic here that you guys should be aware of. Was this cooling tower at an elevated point from this pump? Was the cooling tower on the top of a building and the pump in the basement of the building? No? Okay, keep that in mind. Because like this curve shows, that your pump head drops. You must make sure that there's enough, because a cooling tower is an open loop system, your water has to overcome the vertical column of the pipe, right? It has to overcome a fixed head. Otherwise, the water is going to stall in the pipe and never reach the cooling tower. Fluid mechanics, fresh junior year, right? That first thing you learn, HF equation. You guys all know what I'm talking about. At least the juniors and seniors should, and the PhD kids should. Students, not kids. So you have to remember, if this cooling tower were, say, on the top of the LDS office building in downtown, and the pump's at the basement, that building's 200 feet high. So even though you could trim it down to 160, let's say, Nathan, when you get to 160, that water is not going to get to 200 feet high. That's just vertical head that it has to overcome. Now, if the cooling tower and the pump are both on slab at the same gradient, you avoided that. You just need to have NPSH so that your pump doesn't cavitate. But keep in mind that when you're dealing with cooling towers, you are moving water that are at elevation. You're moving water up a vertical open column. And that's just lift. And you have to make sure that your head volume doesn't get too low. Okay? Your pump head doesn't get too low. Clear? Cautioned enough so that you can harass Julie and Cody about what I just told you. Okay.
I think one thing I want to add to that is like, it's easy to slip into the habit of not caring about what Sunny just said, as a lot of times as IAC students, the question we're worried about is, are there energy savings or not? That's what you care about, right? Because that's your job. On the flip side, when you're dealing with customers and clients, they don't care so much about that. They care about, is this going to disrupt my process or not? So even though you don't have to think about this kind of stuff from your energy save, of course, out of VFD, you're going to see energy savings, easy. You have to think about, the engineering side of it, if they're to see if they're actually going to implement it, right? Because if it's going to disrupt their process, they're not even going to take a second look at it. So just kind of a shift of mindset there.
Yeah, it's about feasibility of the project and your reputation, right? Because that's what's going to happen is this project, Michael Reynolds, this project, if you implement it, you've promised the moon, and you're going to come back and find out that, oh crap, this $40,000 investment just didn't achieve what it said was, because we forgot to count up this little fluid fundamentals called head, right? So that's important. I have seen this happen. I learned this the hard way. So this is lessons from the School of Hard Knocks. Let's go back to your questions, Brooke. Okay. How to find pump curves from nameplates? Get the model number, get the serial number, call up, go look up online or call up the manufacturer and they will give it to you. The beauty about model numbers is you'll find that information online invariably, even if it's a 20-year-old pump. Now, if it's a 40-year-old pump, you're going to struggle, but a 20-year-old pump, as soon as it was the turn of Y2K onwards, you've got data archived online. The serial number is particularly valuable. The serial number is unique to each pump. You can call the manufacturer and they have information on that serial number. And that serial number will give you exactly what the trim was on the impeller. So the general pump curve, like was shown in that slide, you'll get that, but you don't know exactly which line you're operating on. But the serial number will give that to you, and you had to call the manufacturer. And in our office, we got a guy who is very, very comfortable and knows all the manufacturers, and we literally go to him nationwide, because let's say it's a Bell and Gossett pump that's in Florida, but if I get the serial number, I can call up the Bell and Gossett guy here and say, hey, for this model and serial number, can you pull out the curve? And it's in their database. So we tend to, in our office, be able to support our national offices because of that connection. So it's a very valued connection to have with manufacturer reps. Are you screwed if you don't have the pump nameplate? Yes, if you don't want to take measurements. No, if you're okay with taking measurements. It's as simple as that. Because if you don't have the nameplate, you can take amp readings, you can take pressure readings, you can do field diagnostics to get that information you need. But having the nameplate is going to help you out a lot. Now, if you don't have the nameplate, because often it is encapsulated in the insulation, find the mechanical drawings. They're there somewhere in that building, I promise you. If they're not, they will be there in a mechanical room under the air handler, under the cooling tower, completely rotten and molded over. Dig it out, put a respirator, and find that information. Spending that 10 minutes to get dirty and find that information can save you many, many hours of pain and data logging. But your worst case is to actually do it. Or you can take a gamble and ask the operator, a wise woman said, trust but verify. Yeah, there's James for you. He's only done this for a year.
I mean, if you ask the operator, he's probably going to tell you what he thinks the pump flow is, yeah, but it may or may not be right. So
yeah, they generally, to James's point, they will know the motor horsepower of the back of their head. They may not know the GPM and the impeller diameter of the back of their head, and so that's where you end up. So from a VFD project onwards, James is absolutely right. You got the VFD. VFD is connected to the motor, not to the impeller. So as long as you've confirmed that you don't have a head issue, you don't have to do any trimming on the impellers, you're good to go with just the motor nameplate. And that can be, like James said, found out from the operator very, very easily. Thoughts on including demand savings? Demand savings, I do not use them on VFDs. The reason being is that all that has to happen in a given billing cycle is that pump has to ramp up to 100% for 15 minutes. And then the demand savings are gone on the bills. That is what I like to do, under promise, over deliver. I take that as my little goodwill cherry on top, because they get the demand savings. Will they see it on the bills? Absolutely. But there is the off chance that on a VFD, you may not see the demand savings because of how it's run. Okay. Thoughts on appropriate use of affinity laws? We use it all the time. The cubic relationship, that last slide, or the second to last slide, that's perfect. We just use that on our daily. Only thing we do is that there's a that's an ideal affinity law. It's a ideal cubic law, we use a 2.4 or 2.7 relationship in the real world. So I would have used 2.4 to 2.7. I have validated 2.7 using data in my own projects that I have solved for that function, that cubic point, and come up with 2.7. So I feel very strongly about using 2.7, 2.4 if you want to be more conservative. But that's the number I would use in real life, 2.4 to 2.7. Take your pick. Any other questions?
Perfect.
Hey, team, I'm going to jump in with one for Sunny and James. One last one before we go on to the next group. Sunny, James, I'm just curious, based on the costing that you saw there, what is your sort of, based on your current market context and what you're seeing, what do you think about the pricing that is being used?
You're muted, Sunny.
200, 250 is not bad on a per horsepower basis for equipment. Labor, I like that multiplier one or 1.5. It's almost material and labor is now equal, and with today's rates, labor could be 1.5. I think the controls is where it'll get you to implement this project, especially because you've got a two-dimensional control measure going on here, as is proposed, and they could fight each other. So striking the balance there, that might be a little bit more time consuming than you estimated.
Okay, fantastic. Well, I'm guessing that your input and advice here really helped that team. So thank you for that. And let's move on to the second group then, and talk about that topic.
So one last thing, you could, on your costing, always use the RMP incentives to showcase that
Absolutely,
buy
yeah.
down, and the incentives have gone up, Julie, as of January 1. They're now $200 a horsepower. So it's 3x what you and I used to work in.
Okay, great.
So
Please note that, team. Make sure you include that when you're sending me draft information. That's great, Sunny. Thanks for that update.
yeah.
Okay, I think it is my group's turn to present. Let me share my screen. I think now I need to present, slideshow, present to a meeting. Or does it just work like this? Can everybody see my screen? Are we good to go?
Yep.
Awesome. Okay. So we're going to start off. Here's our team. We have Trey, Connor, Jessica, myself, and Paola. And you can see each of us had our own little job that we were in charge of to make this presentation work.
Parker, say your team name again.
I actually have forgotten our team's name.
Oh, that is not a good
members help me out. We're LLC4. I forgot her name. Anyways.
Looking like true engineers.
So yeah, we're just LLC4. Here we go. Background information. I think it's going to be easier if we start with kind of this process flow, so everybody can understand kind of what we're thinking with this AR. And Trey was in charge of this process flow, and he'll kind of describe kind of what's happening here with the process flow.
I'll jump in because this is definitely a part that I had to have Connor draw me like 4 or 5 times so I could understand that there were 2 different loops. So basically, we have the, we'll start at the cooling tower. We have the cooling tower that is then connected to one of the air compressors that cools one of them, and then also cools both the chillers, and then, recycles it back in, cools the water, does that loop. The second set is just the chillers loop. So the chillers export their heat to the cooling tower loop, and then they cool various processes they use in the facility. I think there's other things that they use, but we're more worried about the air compressor. So it does one of the air compressors, and that's that chiller loop.
So our recommendation, what we're using is we're going to put that second air compressor onto the cooling tower cycle. So the chillers won't be cooling the air compressor, it'll be all the cooling towers, is what our recommendation would be. So here's some background information. Like I said, it has 2 chillers, which are being used for process and HVAC. Then they have that cooling tower, which I believe is just to work with the chillers and the compressor. And then the compressor are screw air compressors. And those are the background information. We are still waiting on a lot of data to come in. So we've been making a lot of assumptions with this AR. So as we go through, we're going to be talking about how we've made a lot of assumptions and we're not very confident as of right now with some of our methodology, just because we have to assume a lot of things. So kind of our proposed methodology, and again, this is kind of hypothetical because we don't have a lot of the data we were hoping to get. So we were kind of thinking, as of now, we don't have any data from the chiller system and it's kind of up in the air. We do have the nameplate, but other than that, we don't know how often it is running, kind of the schedule it is running. So a lot of that has to be assumptions with the chiller in the process is what we've been told, and we're waiting on that data. So what we're thinking is you can get a rate of how much kilowatts it takes to cool down the water in your chiller. So like the energy from like gallons per minute per kilowatt hour. And then from there, you can tell how much energy goes in to cool the water. And then from there, we can estimate how much water is actually going to the process and then how much of that chilled water is going to that one compressor. Because we don't want to change the cooled water going to the process, only to the compressor. So then once we estimate how much water is going to the compressor, we can then say that is our energy savings, by then determining all that same things with the cooling tower. How much energy goes into each gallon per minute of water to cool it. And then we can just take the difference of the both, and that will be our cost savings. So some of the assumptions is we don't know how much gallons of water the chillers are producing. We don't know how much gallons the cooling tower is also cooling. So those have to be assumptions. And so a lot of these are just based on assumptions that we don't know quite yet. And we need to kind of, I guess, use the nameplate or other ways to figure out how much water is being used and how much electricity is being consumed by the chilled water system. And then once you get all that, you can do the implementation cost, which is kind of easy. All it is just buying piping, where you can then add the extra pipe and connect the water, the cooling tower water system into the second compressor. And that's about all you have to do. So you just have to buy the piping and then somebody has to install it. So this is kind of what we think the implementation cost would be. I guess you can check to make sure that the water isn't running too hot for the compressors and just make sure everything's running smoothly. So that is our implementation cost. And one thing that we need to note to the team, whoever's doing this AR, is to make sure you can find the diameter of the pipes that they're using and also how much pipe would be needed so we can make a better rough estimate on the implementation side. So the questions is, we are still really confused on how to go about kind of scaling the chiller, because we know that the chillers run less, will run more in the summer, less during the winter, but we don't know a good way how to scale that without getting a lot of data from the company, or like getting a trend data for a whole entire year. So we're kind of stuck on how can we scale our data for the chillers so that we can say in the summer they run less and in the winter they run more. So I don't know if you guys have any other thoughts on that one. And our second question is, in our proposed method, we neglect the difference in temperatures of the water. However, would this affect the compressor's efficiency? So we don't know if, because if we run it from the cooling tower, it would be hotter water going into the compressor. So we don't know if that will actually lower the compressor's efficiency. So we also are kind of stuck on that one as well.
Okay, so I'm going to take your second one because that's a quicker, simpler answer. Probably yes. Likely not much. You're absolutely right that, compressors, the cooler the water that to cool it, a cooled compressor works more efficiently. However, there's a minimum floor to it, right? You're providing, let's say 44, 45 degree chilled water to it, and the cooling tower, using the wet bulb rules, maybe giving it 75. The delta gain in efficiency between 75 and 44 might not be as much as if it were an air cooled compressor that was, 100 degrees to 75, right? So it kind of hockey sticks. 100 to 75, you could see a lot of efficiency gains, and that's what we do with compressors. Is we want to bring in colder air to it to compress it. We want to cool it and operate it in a cooler environment. Off the top of my head, I am not a compressor guru. The guys at Cascade are much better at that. But so I don't know how much of a difference it would make between condenser water temperature, that's cooling tower water, or chilled water temperature, that delta on the efficiency. My suspicion is not much, but it is definitely something to think about and at least cross-check with the literature. If the cooling tower or the chiller compressor manufacturer says, water cooled water, it'll have an efficiency curve associated with it that says it pulls 1 kilowatt per 4 SCFM at 75 water, and it pulls 0.92 kilowatts per 4 SCFM, standard cubic feet, or it's AFCM, one of those two units, at 44 degree water. You can look at that compressed manufacturer's catalog and figure that out. But it's, your thinking is on the right track there. Okay. How would we go about? Okay, so first, let me give you 2 quick rules of thumb. Go back to your chiller drawing.
This one?
Okay, yeah. So on your chiller loop, 2.4 GPM equals 1 ton of cooling. Okay. Rule of thumb.
Okay.
A chiller will chill 2.4 GPM per ton. For heat rejection, you need 3 GPM per ton on the cooling tower side. So you're moving 2.4 in the chiller loop, and you're moving 3 GPM in the cooling tower loop. Okay. So if you have your pump size, and let's say your pump gave you 250 GPM on the chiller loop, then I can by default tell you that your chiller is approximately 100 tons each.
Oh, okay.
See that dirty little trick? Now, if I know that the condenser water pump was 300 GPM, I also can deduce that it is 100 tons on the chiller side. So as long as I know one of the pumps here, I can, without the nameplate, kind of figure out where it is. If you have the cooling tower nameplate, and that tells you 100 GPM, then you can backtrack your way all the way to what your loads are. Okay. So hopefully that trick gives you a little bit of guidance on how to figure out your capacities. Next, I'll go back to your questions now. Okay, so there's your scaling, there's your tonnage side. So we figured out the ton. Now you need to know what's the kW per ton for your chiller, right? Okay, so once you know your tonnage, how many of you are familiar with eQuest or Energy Plus? Anyone? Hey, Julie, do we do any energy modeling in this class?
No, probably. If anything, it's self-taught, and I know Michael spent some time self-teaching himself, but there is no formal training.
Okay.
RT and I are fairly involved in Open Studio, and I know some eQuest as well.
Okay, so I don't know if these guys are in your group, but these guys are golden right now for you. All you have to do is get them to open Energy eQuest for you, and there is a performance curve, a biquadratic performance curve that is standard for all chillers that's provided for you. And there's one for a centrifugal chiller, water cooled, one for a screw chiller, one for a scroll chiller, all of the chiller types. You can get the performance curve, the coefficients from there, and the biquadratic equation from there. And then it's basically a function of chilled water, and that biquadratic is a function of chilled water temperature and ambient wet bulb temperature. Aha, condensing temperature, right? Ambient wet bulb temperature is connected to condensing temperature and outside air temperature. Keep coming back to psychrometrics, people. You can create your analysis for an annual year by using the bin method. Do you guys know about the bin method?
Some do, yes.
Okay, so find the people who know about the bin method, use the biquadratic equation, and then multiply it by 100 tons, and you will get the kW per ton times your 100 tons, and you will get the energy use for any period, any time of the year, based off ambient condition. Did that help anybody? Or have I lost you completely?
I think it makes sense to me, and it helped a lot kind of determining how much energy is being used, and also with the time of year. I think it helped a lot.
Okay, so your chiller is going to run that way. That's for your chiller, because all you need is a kW per ton as temperature varies, right? Wet bulb temperature or dry bulb temperature. On the cooling tower, it would just be, hey, my cooling tower is rated for 100 tons. I got 70 tons of heat to reject. So it's cycling 70. And you could just use a 70% multiplier times your fan horsepower, or you could subject it to a fan curve with a VFD, and you can calculate the energy use, just assuming that, right? That if 70% of the load is there, it's going to cycle on only 70% of the time. That's a reasonable assumption to make in energy analysis. Fair enough? Does that answer that question?
Yeah, that does.
So now you got your chiller energy and your cooling tower energy for that. So you're going to have that. There's a lot of feedback there. So the other thing to think about is, if you go back to your diagram, is that you really don't need to worry about cooling tower energy use. You can almost ignore that in this entire analysis, because all you're doing is the air compressor is rejecting X number of BTUs into the chilled water loop. The chiller is taking those same X number of BTUs and rejecting it into the cooling tower loop. And the cooling tower has to reject those X BTUs of heat to the atmosphere. X is equal to X is equal to X, right? So the cooling tower energy is almost going to be a wash. So your real gain is moving those BTUs from a kW per ton over to a cooling tower. And it's the kW per ton between the chiller and the cooling tower in terms of cooling that you're evaluating. You will find that your cooling tower in your proposed model should have, will maybe run a little bit more hours duty cycle, but BTUs would be the same.
Okay.
One translation of that, Parker and the team, is it's not a big factor, but there will be some energy penalty. The difference between the savings and the penalty are nominal, but what Sunny's saying is there will be some energy penalty because there'll be more load on the cooling tower, which will cause the fan to run a little bit more.
Yeah. How big is this air compressor that you're trying to move over to the cooling tower?
You remember the horsepower ratings, Trey?
It's 200 horsepower, I believe, is both air compressors were.
Okay. So it's a decent size air compressor. How physically separated is this air compressor from the cooling tower?
They're like right next to each other.
Yep. Location-wise, Sunny, it's pretty good.
Oh, okay. Okay. Because normally when I would see it this way, it would suggest a large physical separation. So is there a reason that they didn't put both those air compressors there in the first place? Have
Yeah.
any asked that
I
question?
believe the case was they added an addition to the building, which when they did, they put the new air compressor on the cooling tower, but left the previous air compressor on the chiller loop.
Did so they may have had air-cooled condensers but chillers first and then switched to water cool and added that whole water side later. And that might be why you have it this way. That might just be worth asking about. Is if that was the source, that would be a curious thing to know.
Generally in this case, Sunny, it's pure speculation because we're working with people who have just inherited the building. So
Okay.
probably not a lot of historical information going to be super valid.
Okay. And you have the nameplate of the air compressor? Yeah. So the first thing to do is check whether that air compressor can run with cooling tower water, which will roughly be 75 degrees, 65 to 75 degrees, versus chilled water, which is probably 45 to 50 degrees. Because if that air compressor was perfectly matched to run with 50-degree water, then again you come back to the feasibility versus energy savings issue, because that might mean, hey, we got to retune this whole air compressor or buy new. They may have special ordered that air compressor to run with chilled water. Okay, what other
Thanks,
questions,
Parker.
sir?
Other questions, Parker or Trey or anybody else on the unmentioned group 4?
I think, at least that's all the questions I have. I don't know if anybody else has any other questions.
Sunny, I'll just ask in general, like the other one, if you'll comment on their thoughts, their proposal here for costing.
Let's go back to that slide, Parker. Professional for piping costs. Yeah, I think you would be surprised with piping costs. Also, you might have, as you pointed out, diameter differences that start to really play games out there. You may also have to think about adding a pump, because you've got to move water through the cooling circuit of the compressor. So that's an increased head loss, right? More losses. So you may have to put a pump in there now on that loop. It has probably size for one air compressor. Now you're bringing in a second air compressor. Kind of need to think about that.
In fact, Trey, I would suggest you default to assuming you have to add a pump. It won't be
Yeah.
huge, but I think showing some energy penalty and cost for that would be good.
Yeah, and it would show thoroughness and thought process there. I don't know if a pipe fitter is getting paid $250 an hour. I'll change my profession as well. I think pipe fitters are getting paid between $100 to $125 an hour. Controls people are getting paid about $150 to $180 an hour, depending on, are they installers or are they doing M&V, right? So a controls tech out of Harris Mechanical is roughly billing for about $150 an hour. A certified pipe fitter is about $110 to $125 an hour. So those are going rates, normal Monday through Friday, 40-hour weeks. So if the reason I state that is if this has to be done nights and weekends, multiply by 1.5 or even up to 1.7 for overtime rates and graveyard shifts. And yeah, your pipe dia has to be cross-checked really well, because that can come and bite you in the butt with the pumping. Go back to your drawing. I'm hoping that your chilled water loop is just water and not glycol.
Sunny, explain.
Okay, how cold is this chiller? What is the various process on your chilled water loop?
Trey, you want to jump in?
I do not actually recall exactly what else was on there.
They're not making ice cream. It's not below freezing.
No, it's actually
No.
Gentle Products.
Okay.
So they're trying to keep their chilled water loop to somewhere between. They recently raised it to 45, if memory serves, from 42 and a half.
Oh, okay. The reason I brought that up is chilled water is water. It starts to freeze at 32, as you all know. And typically chillers will turn off at 39 degrees if the water loop is 39 for freeze protection, because that is too cold. But if but there are ice rinks and other facilities that are designed to be below 32 degrees. And in that case, they put antifreeze, glycol, antifreeze, right? That's all there is to it. And that allows you to chill that fluid now to below 20 degrees and still maintain it in fluid media. The reason I brought that up is remember, you're going to have to cut a closed loop. Your chiller loop is a closed loop. So when you cut that open to remove the compressor, you've also got to seal that back up. And if you have glycol and you bleed, and so when you cut this part up, you're going to lose some amount of water. I don't know how much. If it ends up being a large volume, then you have to get that chemistry of that water back into play. Otherwise, you can start having many things grow inside that water if it's not spinning. And then there's cost, and especially if it's glycol, and let's say you lost 200 gallons of water in this loop and 30% of it's glycol. Well, you got to buy 60 gallons of glycol now, 30% of 200. And so there's cost associated with just cutting this here that could come with the water that may be lost in the process. And so knowing that it's water or it's a glycol, 30% glycol solution is important, because if it's water, it's easy, it's cheap. If it's glycol, that starts to add some cost to it to be accounted for.
And Trey, do you remember if this is glycol or not?
I'm fairly certain it's just water.
No, actually, it's a mix.
Is it?
Contains glycol.
Yep. Good stuff, Sunny. Thank you again. Nice job, team. I hope the next time you present, though, you remember your name. It looks like everybody was somewhat interested because it's 5:15 and many of you are still here. So this has definitely been a good conversation this week and last, Sunny. So thank you for that. I think each one of the teams got some good advice on how to move forward next. So appreciate that. And for now, I think we can say goodbye and